Welcome, everyone. I'm Saurabh. I work on PyTorch at Meta, and I'm joined here by Gerson, who comes from Google. And together, we're going to talk about some of the scaling bottlenecks for fault tolerance and various solutions that we developed to resolve those. So in a training job, even though we take checkpoints periodically and we restore the training progress in the event of a failure, there's still a non-trivial amount of GPU or wasted GPU hours. One reason is the checkpointing overhead itself. So if we may not want to take a lot of checkpoints. The second is the unsafe training progress, which is the red block here that you see. And it can be as bad as the checkpointing interval itself. And it has to be multiplied by the number of GPUs in the job. So for large-scale jobs, we want to minimize this checkpointing interval as much as possible, which means that we may want to take as many checkpoints as possible. So you can already see the trade-off here. So more visually, if we plot the wasted GPU hours or wasted training time against the checkpointing frequency, the curve looks something like this. So if we are checkpointing too frequently, then the wasted training time goes up because of the checkpointing overhead. And if we are checkpointing too infrequently, then again, wasted training time goes up because of the larger window of unsafe training progress. So for large jobs, we want to take checkpoints very frequently, but at the same time, we want to reduce the checkpointing overhead to near zero. So what are the different overheads during checkpointing? So I am taking the example of the asynchronous checkpointing here, because I'm assuming anybody who cares about training efficiency, they must already be using asynchronous checkpointing. In there, except staging, all other steps in the checkpointing, like the metadata preparation, planning, I/O, upload, all those things happen asynchronously. Now, during staging, we offload the data from GPU to the host memory, and that's why there's memory overhead. We allocate and deallocate the memory for every checkpoint save, and also it's pageable memory, so page faults also happen, leading to inefficiency. And again, this is a blocking operation for GPUs. The next step is the planning step, where we figure out how different data types need to be serialized and saved in storage. And we also prepare the metadata. So there is metadata preparation cost here. But the main bottleneck here is the collective. So rank 0 coordinates across all these different ranks in the job, and it gets their local metadata. Then it does validations, deduplications, creates the global metadata, which describes the entire checkpoint. And this collective, what we have observed is it becomes quadratically more expensive with respect to the job size. And in the I/O step, we observe that the GPU utilization gets impacted because of the global interpreter lock contention between the trainer threads and checkpointing threads. So on the right, you can see the plot of GPU utilization. And the red line in the middle demarcates the time when staging has completed. And after that, the GPU utilization should come back to the previous baseline. But you can see that it's suboptimal. It's less than expected. And finally, the checkpointing can only happen as fast as the storage bandwidth allows, right? So there are storage bandwidth constraints as well. So we developed various optimizations. For staging, we now do pin memory-based staging. So the memory is page locked, so we don't run into page faults. Also, another interesting idea here is that during the forward step of the training, weights do not change. So we overlap the staging step with the forward step. So effectively, the staging becomes partially or completely asynchronous. For the planning step, we introduce the rank local checkpointing, where every rank saves and restores its own data and metadata. Another interesting idea is that across different versions of the checkpoint, the metadata that describes the checkpoint, that does not change. So we can cache the metadata in all these runtime objects, and we can amortize the metadata preparation cost across different checkpoint saves. Finally, for I/O optimizations, we built the process-based checkpointing, which completely eliminated the GIL contention issues that I described earlier. And for storage bandwidth constraints, we built in-cluster checkpointing, where we stage and replicate the checkpoint within the cluster itself. To provide more technical details, I'll invite my friend Gerson here, who will talk more about it.
Thank you. One of the reasons we were excited to collaborate with the Torch GCP team was so that we could bring some of the latest and greatest checkpointing optimizations to our customers on Google Cloud. I want to provide some more color in what it's like to train on cloud and how to measure efficiency. Cloud customers want to maximize their return on investment, right? And care a lot about raw performance metrics, such as MFU, tokens per second, step time. These are great metrics for understanding the overall model's efficiency within a short period of time. As you have larger training jobs, due to the sheer distributed scale of these workloads, customers will run into unexpected failures and fault-tolerant issues. Due to the highly coupled nature of AI workloads, when one node goes down, the entire training job stops making any progress. And this really emphasizes the overall importance, or the importance of overall performance, right? We don't only care about performance at a single step time, but the performance over the course of the entire training job. We define a metric Goodput for this. And to understand Goodput, there's a visual on the right. The bar represents the total time spent training, where 80% of the time is spent training at peak performance. The remaining 20% of the time is time wasted due to unexpected interruptions, failures, and stragglers, and things of this nature. We could define Goodput as the percent of time spent on productive training, or 80%. The remaining time is considered bad book, 1 minus 80%, which is 20%. Goodput is important to customers as it has go-to-market implications and could save millions of dollars. Now, tying back in checkpoint. Why is checkpointing so important to Goodput? There are a few reasons here. During stable training, every checkpoint you save has some degree of saving overhead. And this results in slower step times and ultimately longer time to converge. Furthermore, during these unexpected interruptions, you have to reload your state back into HBM. This is loading overhead, which is ultimately time not spent training. And furthermore, you have to revert state to an old checkpoint. Any progress not saved is considered lost, and the time spent trained on these lost steps is considered waste in progress. The async checkpointing optimizations that Saurabh went over are great for minimizing the checkpoint bad put, but alone are not good enough due to existing storage I/O bottlenecks, especially within a cloud environment where your storage is in a persistent location. So we collaborate together to develop an in-cluster checkpointing solution for our customers in Google Cloud and aims to minimize checkpointing bad put. We define in-cluster checkpointing as local checkpoints, being able to save and load checkpoints locally without a persistent storage. Here we see just the cluster itself in which you could manage all of your checkpoints. The obvious benefit of this is the read and write speeds are much faster since you could take advantage of RAM disk. Now you could also tie this in with a more traditional persistent checkpointing based solution to have a multi-tiered checkpointing solution, right? You save your checkpoints frequently locally and infrequently to persistent storage in case of any catastrophic cluster-wide failures. When you add on the Torch DCP async optimizations that Saurabh went over, you're able to push saving overhead to near zero, which allows you to fully utilize and take advantage of the ability to save checkpoints frequently locally. Now, I want to provide a bit of an illustrative example on how in-cluster checkpointing works. Here we have an oversimplified workload of a customer's training job where we have 4 nodes, 2 data replicas, and we have 1 hot spare. You can notice the hot spare does not have checkpointing state because checkpointing state is, or the training state is updated frequently. But now let's say 1 node goes down, right? To resume training as quickly as possible, customers will reserve a portion of their capacity such that when this node goes down, you could swap it back into place. However, you could see node E just swapped in place doesn't have the checkpoint state. Furthermore, in-place reset is not guaranteed. And what is meant by this is that as you swap in and out nodes, your overall network topology changes. And this dictates how you define your distributive collectives and groups. And so because of this, in this example, node A and node C swap positions in our network topology and thus need to transfer state. So with in-cluster checkpointing in our solution, we're able to replicate state during loading time, right? We see node A and C both already in the cluster swapping state, and we also see node A giving its state to node E, such that node E has the needed checkpoints and can resume training. After all this swapping, which takes advantage of the nickel collectives, we're able to then resume training. Now I want to, I hope that built some intuition on how in-cluster checkpointing works, but we also have some empirical results. Here's a plot showing the checkpointing impact on bad put, right? On the y-axis, we plot the overall bad put percentage incurred from checkpointing, and on the x-axis, we show the number of interruptions a day. We could see that as you introduce each of these async checkpointing optimizations that Saurabh went over, we're able to reduce our bad put percentage. Furthermore, with the addition of in-cluster checkpointing, we're able to even further push the bad put percentage closer to 0. I think one of the high-level takeaways here is that in-cluster checkpointing, as well as these async optimizations, are important, and that with depending on how frequently you run into these interruptions, you may need various degree of sophistication. And in the most extreme of cases, with all these optimizations, you're able to reduce bad put incurred from checkpointing by over 50%. That concludes our talk. We're happy to take any questions afterwards. And if you're interested in learning more, we have several links attached to the slide, our blog posts we worked on together, and also like Google Cloud's approach to resiliency and checkpointing. Thank you.